Hey, 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 good evening, everybody. Welcome back. Welcome back. We're so excited to have you all joining us here for another live office hours hosted by Chegg. I'm Dr. Janita Pritchett Clay, or Dr. J, and you can find me at Gen Chem with Dr. J. I'll be your host for this evening's chemistry office hours. A little bit about me if you haven't been to one of these sessions before. I've been teaching general chemistry in some form or another for the last 2 decades. I have a PhD in analytical chemistry and also run a nonprofit that introduces K through 12 students to science, technology, engineering, and math concepts. And we do this through hands-on activities. I launched my virtual platform back in 2020 to help really support students around the world as they navigate their personal general chemistry journeys. So I'm super excited to partner with Chegg to host this live office hours. For those of you that might be new to Chegg, they are here to help to make your academic journey a bit smoother. They have a ton of resources to help you get through school, like online study help, expert Q&A with step-by-step solutions, writing support, and a whole bunch more. And in fact, if you hit that QR code on your screen, you can actually sign up today, get a subscription for 50% off. So definitely be sure to check out that subscription. For those of you who are joining us for the first time, welcome. And for those of you who have been here previously, welcome back. Excited to have you here as we talk a little bit about chemistry. And so I'll be here every Thursday at the same time at 8:30 p.m. Eastern or 5:30 p.m. Central Pacific time to help you all with your general chemistry questions. You can think of this kind of like a virtual office hour. I'm going to be teaching you all different concepts, answering questions or comments that you might have in your chat. So definitely put anything that you want to learn in the chat, and we'll try to get to as many questions as possible tonight. But I'm here to help. And so with that, let's go ahead and get tonight's session started. So a couple of things you want to make sure you have nearby, because we're definitely going to be using them. You're going to want to make sure that you have a calculator of some sort. Today I have a different calculator because I couldn't find my other calculator, but it's all good. As long as we know how to put those exponents in, we will make it work. So you want to have a scientific calculator, so something that hopefully can do scientific notation. You also should have a periodic table nearby. Again, I just printed this off just so that I could reference it throughout the night, but you can use your phone as well if need be. And then, of course, pen and paper if you want to follow along and do some of the problems with me, okay? And so to kick things off, I have a few problems already stored, but I want to hear from you. So definitely put comments or questions into the chat, and we'll be sure to answer as many as we can, okay? And so if you have been with us for the last 2 weeks, we have covered a lot of topics so far. And I wanted to pick up where I left off last time, which is all around naming compounds. In chemistry, we learn about different types of compounds like molecular compounds. Those are compounds that have 2 nonmetals with them. And we also learn about ionic compounds, which often have a metal present and a nonmetal or perhaps even a semimetal. And so when we're naming them, we have 2 different naming formats that we have to apply. And so where we ended off last week, it was learning how to name our molecular compounds. And so I wanted to start there, and then we'll get into how to name those ionic compounds. Remember, when we're naming molecular compounds, we have a format that includes using prefixes to describe how many of each element are present, okay? And so again, this format that we're using applies when we're dealing with binary molecular compounds. So binary means there's 2 different elements. Molecular compound tells us that no metal will be present, okay? So with that format, we start with naming a prefix, and that first prefix is going to describe how many of the first element that you have. So let's take, for example, if we had something like CF4. And so you see 2 different elements. So we know this is a binary compound. Both are nonmetals. So this is a molecular compound. And again, just to help you remember where your metals are, if this is your periodic table, there's that little step in the middle. This entire side over on the left is your metals. This top corner over here are your nonmetals. And then the step represents your semimetals, okay? And so when we're naming it, we use prefixes to describe how many of each atom we have. Now, your typical prefix that you're going to use, for one, we typically say mono. Two, we say di. Three is tri. Four is tetra. Probably thinking, why isn't it quad? But tetra is actually based off of the shape, a tetrahedron, which is a four-sided pyramid. Five is penta. Six, hexa. Seven, hepta. Eight, octa. Nine, nona. And 10, deca. Okay. And so we use those prefixes to describe how many of each atom are present. Now, very important, when we're looking at the first first element, we can use any prefix in that space except for mono. Okay. So we never put mono in this first position. Okay. Then we go on and we name the first element. And then we'll say a prefix to describe the second element. And so the prefixes, again, those same 1 through 10 that I just named off. Then we take the base of the element and then we add the IDE ending. Okay. And so let's try that here with this CF4. And so we see that we only have one carbon here present. And then we have 4 fluorines. Okay. So what we might want to say is monocarbon because we only got one of them. But remember, we never use the mono prefix. So when we're starting this off, we would just simply say carbon. Then we get into the second element. We have 4 of them present. And so now we would say tetra for the 4, fluor, and then we're going to drop the INE ending and add the IDE, ide, okay? And so carbon, again, if we had a prefix here, that would describe how many carbons we have. So we have 1 carbon, so no prefix. Tetra tells us how many fluorines we have, okay? And so did you get that one? Because this is where we left off. We're going to pick up now using the same naming format and helping to solve some of these problems, okay? So I've put a few here on the board for you. And so go ahead and try to tell me the formula based off of the name that we have. Remember, the prefix followed by the first element, and then the prefix, then the second element, plus IDE ending. That's our format. So what would the formula for this first one be? Dinitrogen tetraoxide. Okay, so go ahead, try putting that in the chat. And let me know what you get. And again, look at the prefixes. We see dinitrogen. So that tells us how many nitrogens that we have. And tetra. Whenever you have the 2 vowels together, you can drop the A. So hopefully you see that this should be nitrogen, which has a symbol of N. And we have 2 of them. And then oxide tells us that is oxygen, and we have 4 of them. Okay. Awesome. All right, let's try sulfur hexafluoride. Sulfur hexafluoride. Okay. So again, look for those prefixes. We don't see a prefix before sulfur. So that should tell us the fact that that means there's only one, right? Because we never use mono. That's the only time we don't put a prefix there. And then hexa. Hexa. Think hexagon would be 6. And then fluoride is our fluorine. So we would have SF6. Okay. And then last but not least, we have our diarsenic trifluoride. So again, look at those prefixes. We have di and tri. So that tells us how many we might have. So diarsenic trisulfide. So arsenic. Now this one can get a little tricky because a lot of people might see arsenic and they say, oh, AR as the symbol. But actually arsenic symbol is AS. AR would be argon. and we have 2 of them. And then trisulfide, sulfide means sulfur, and we have 3 of them. Okay. All right. So again, this is where we left off. We're going to add another layer to our naming. Okay. So remember, this format that we just went through, this is only when we're dealing with molecular compounds, binary molecular compounds, meaning no metal present, and there's only 2 elements. Okay. All right. So let's get into what happens when we're dealing with ionic compounds. Okay. Now, ionic, again, this format we're using is for binary ionic compound. So binary means 2 elements. Ionic, we learned ion last week. And so ions, remember, those are things that have charges. Those are things that have a charge because they've either gained electrons or they've lost electrons. And so you have these positive and negative attractions that are there that are able to get those atoms bonded together. That's different than a molecular compound where covalent bonding is happening and we're sharing electrons. But because of that, the type of compound that you have, you end up with all these positive and negative units that are bound to one another. And what we report out as the formula is actually what we consider the simplest whole number ratio between those ions. Okay. And so a couple of things to remember or to note when you're dealing with an ionic compound. I'll say about 98% of the time that you're dealing with an ionic compound, you will have a metal present. Okay, so again, periodic table, got your step. Remember, your metals are over here. So these are semi-metals and your non-metals. So kind of a quick test that you want to look is, do I have a metal present? And I'll show you some examples of that times when a metal won't be present, but you'll have a very clear other type of ion present. Okay. So the first question you ask yourself is, do I have a metal present? Okay. And so if you have anything that's found on the left side of that step on your periodic table, yes, you have a metal present. So you're not going to use those prefixes anymore. Okay. Instead, what we have to figure out is, well, if I have a metal present, is this a metal that only has one charge? Okay, meaning that it only has one possible charge that it can create. And there's a certain elements that applies to. Okay, and so if you have, and so you'll want to remember this little group here. If you have a metal that's in group 1, which are your alkali metals, group 2, which are your alkaline earth metals, aluminum, zinc, scandium, or silver. Okay, so group 1, group 2, or those 4 elements that are present. Those are the elements that they only have one possible charge. Okay, so anything in group 1, remember we learned about valence electrons. Group 1 has one valence electron. It's easy to kick that one valence electron out. So everyone in group 1 likes to take on a positive 1 charge. Okay. Everyone in group 2, remember they have 2 valence electrons. They want to kick those 2 valence electrons out. And so everyone in group 2 will have a positive 2 charge. Aluminum will always have that positive 3 charge. Zinc will always have a positive 2. Scandium, positive 3. And silver, positive 1. And part of that has to do with where those electrons are located, how far away they are, and how much easier it is to get rid of those few. If you're dealing with any other metal, that means that that metal could have multiple charges, right? Like for instance, iron can be positive 2, could also be positive 4 because it's able to go in deeper into the electrons that are present and kick more out. Iron can be positive 2, positive 3, so it can have all these charges, okay? And so you're going to want to memorize this group, okay, of fixed metal charges. Because when we name these, we have one format. When we're naming any other type of metal present, we have to do one extra step, okay? And so when we're naming binary ionic compounds, first thing you check for is there a metal present? Next thing you check for, is it one of my fixed metals? Group 1, group 2, aluminum, zinc, scandium, or silver. Now, when you're naming this, you're going to name the cation, which is the positive element or the metal first, okay? Then you're going to name the anion, which is typically your nonmetal, followed by the IDE ending, okay? So for instance, if we had something like NaCl, well, we go through those tests. I only have two elements. I do have a metal, sodium. I have a group 1 metal, so that means it's fixed. So when I name this, I'm not going to say sodium monochloride because we don't use those prefixes in ionic. I am instead going to just say sodium chloride. Okay. All right. And we don't, anion, we don't use the monosulfur because mono is considered in that in the first position in that previous problem. Because in binary molecular compounds, that mono in the first position is considered to be a bit redundant. And so we don't use mono in that first position. You can put any other prefix in that first position. I think you're talking about the SF6 example that I did previously. This one here. So here we don't use mono. You never use mono in this first position. You can use it in the second to describe the second element, like carbon monoxide, but we never use it in the first position. Okay. Hopefully that helps. All right. Now, what if we're trying to name something like this? All right, FeO. All right. So let's go through the kind of test that we have to ask ourselves. It is 2 elements, so we know it's a binary compound. We do have a metal present. We have iron, right? But iron is not one of those fixed metals. It's not in group 1. It's not in group 2. It's not aluminum, zinc, scandium, or silver. So because iron can have multiple charges, we actually have to do a little math to figure out what charge it would have. And then we're going to include that charge in how we name it, right? So if we look at something like this versus this, Fe2O3, both of those compounds have iron and oxygen in them, right? So we have to have a way to differentiate between these, right? They're both not iron oxide. We have to figure out how to state which particular charge is present, okay? And so what you'll do when you're dealing with this type of situation where you have this variable metal charge, we're going to have to use the other element, the nonmetal, to help us out a little bit, to figure out what the charge of that metal would be. Remember, in an ionic compound, there's something that's positive and something that's negative there, okay? Your metal will be typically your positive ion, your cation. Your nonmetal will be your anion. So you're going to look to your nonmetal, find the group that it's found in, okay? And then use that preferred charge based off of its valence number to help you figure out the other one. Okay, what do I mean there? Well, oxygen is found in group 6, right? Group 6 on your periodic table. So that means it has 6 valence electrons, which means that it's going to be difficult to kick those 6 out to form an ion, but it's a lot easier to try to get 2 more from somewhere else, okay? So oxygen is going to gain 2 negative electrons. So because of that, oxygen has a -2 charge, okay? Group 6, -2. And so, well, how does that help us out? Well, remember, FeO, I didn't put a charge on that compound overall, so it's neutral. So my positives and negatives are balancing each other out. So if I have oxygen is equal to -2, that means this iron has to be positive 2. Because when I add up all of my positives and all of my negatives, they should add up to 0. So 2 plus negative 2, that adds up to 0. So that would check out. So when I want to name this one, I'm going to now say iron. Then following the metal, the cation, I'm going to put the charge of the metal in Roman numerals. So iron 2. And then you follow with the anion, oxide. Okay, perfect, anion. All right, so try the one above, Fe2O3. What would that one be? All right, because now if we look at this, it's different, right? Well, the same rules apply. We don't know iron, but we do know oxygen. Oxygen is group 6. And that's the great thing about this. Once you've done it once, you kind of know what the non-metal will be. Oxygen will also, in this case, still be negative 2. And so now we got to figure out what the iron would be in this compound. And so we could do some math here. We could say, well, I have negative 2 for oxygen, but there's 3 of them. And I don't know what my iron is, right? But I know I have 2 of them. So 2 times x, that equals 0. And so if we solved for x, bring over your 6. So this would be negative 6. So that would be 2x equals positive 6. Then we divide both sides by 2. X would equal positive 3. All right. Now, something cool that you can do. So you see how this is a 2 up here? We know that for oxygen. Because we see a 2 right here, we can cross it back. And so if we do that, cross that back, that tells us what the charge of the metal would be. That cross back method only works if you see the charge of the non-metal present. It's basically, doing the cross multiplying math for you. But if you're not sure if you can do that, by all means, do the algebra. Okay. And so now we got to name this. All right. And so because we have figured out this is a 3 charge, we would now say that this is iron, parentheses, 3 oxide. Okay. Did you get that one correct? All right. So something you want to be mindful of. Notice that I put the 3 and the 2 in the Roman numerals, both as Roman numerals. If you would write this iron 3 oxide as the answer, that would be incorrect. Or if you said iron trioxide, that would also be incorrect. And so you want to make sure you're following that naming formula properly. Okay. So we'll try a couple more just to get some more practice with this. Again, ask any questions away in the chat. Okay. Uh-oh. All right. So there's a bunch here you can choose from. We'll do a couple. We won't do all of these. But let's start with the beginning. KCl. Okay. How would you name KCl? Okay. First question, is this a molecular or ionic compound? Well, it's ionic because we have a metal. What metal do we have present? We have K, which is potassium. Potassium, if you go to your periodic table, is a group 1 metal. So because it's group 1, remember that tells us it's a fixed charge. That means we don't have to worry about doing the math to find out what the charge is because it's always going to be the same charge. So what would the name for this one be? KCl. What would you name this? Okay. All right. So for KCl, we are going to say potassium and then chloride. Okay. All right. All right, let's try number two. Number two, MgBr2. So MgBr2, magnesium. Well, we know we got two elements, so it's a compound. It's a binary compound. Magnesium, Mg, is a metal. And our metal here is a group 2, right? Metal. So again, group 2 tells us that it is fixed. The charge doesn't change. And so now when we name this, we're not going to use dis or monos or anything like that. We're just going to say magnesium. And then bromide. Okay, good. Okay, we're going to do one more. And again, you can try some of these other ones at your leisure. But let's try the number 4. And there's actually a typo. That should be, I'm going to scratch that out, P lowercase b O 2. Okay. So how would you name this one? Okay, so PbO2. Go through that process. We got two elements, so it's a compound. Do we have a metal present? You should be saying, look at your periodic table, find Pb. And when I find it, Pb is right here. Okay, so it's under the step, but it is still a metal. Okay, so we do have a metal. It's not group 1, group 2, or zinc, scandium, aluminum, right? None of our, or silver. It's not a fixed metal. So that tells us we have to solve for the charge to name this, okay? So go to the element that we do know. We know oxygen, group 6 would be 2 minus, right? It's going to take on that -2 charge. So then what would lead be in this case? Pb is lead. Remember, because it's an ionic compound, the positive values, the cations, and the anions have to balance each other out. So in total here, we have -2 coming from oxygen, but there's 2 of them. So that means we have a total of -4 charge on our anion side. So to balance that out, that means Pb has to be +4. So this is one of those scenarios where the cross back method would not work because I don't see my 2 here to help cross back. And so we would just do the math. Okay. So when we name this, this would be lead. Now we want to write 4. Remember, it's not going to be 4. We got to write it as Roman numeral. So lead 4 oxide. Okay. All right. Good job. Hopefully you were able to get those solved. I do see a question from Dino Say, how to take the derivative of 3D vector that is orthogonal to the cross product of the origin raised to the e raised to the x. So I think that question is a bit outside the scope of what we're doing in this virtual office hour. Definitely, we'll see if we can swing back to that. But I think that's outside of the scope of general chemistry. Orthogonal things are always fun, but that definitely not in our Gen Chem class. Okay. All right. So again, feel free to drop your questions in the chat. Again, I do want to remind you all there is a QR code up in the top corner. You can scan that at any time to get access to how to subscribe to Chegg. And there's also a discount promo code going on right now where you can save 50% off. So definitely check that out. So while we're on the topic of naming, I wanted to take some time to also bring up one other part that is one other topic that's part of the naming system, which are these things called polyatomic ions. Okay, so polyatomic ions. Polyatomic ions, if we break down that word, poly means many. Atoms, atomic means atoms, so many atoms. Ions, so many atoms that have a charge, because ions mean charges, okay? And so polyatomic ions are these groups of ions that exist that have more than one element present that have a set charge associated with them. Okay. And so most of the time, your teacher probably is going to ask you to memorize these. And so I suggest get some index cards, put the name that you see on the left hand side on the front of the card. And then on the back of the card, write out the formula and the charge. Okay. So, like for instance, if I'm writing nitrate, I'm going to write NO3 with a minus sign, meaning that that group has a -1 charge associated with it. Okay. Put them on some flashcards and just try to get them memorized. So when I was learning this many moons ago, I put them on those index cards, and then whenever I would be maybe on the metro, or if I had some downtime between studying and whatnot, I would just flip through and quiz myself. The more comfortable you are with these, the easier it will be whenever it comes down to naming, because you're likely not going to get these provided to you on any type of exam. You're going to have to know these, okay? But there are some tricks that you can see that exist here, okay? So something you might notice if you look at something like nitrate versus nitrite, or chlorate, chlorite, or sulfate, sulfite, okay? What you should notice in the nitrate versus nitrite, sulfate versus sulfite, the ate versus ite, that the ate version of that ion has one more oxygen present compared to the ite version, okay? Now, doesn't mean that anytime you see 8 and 8 that you have a set number of oxygens, but the difference between one or the other will be by 1. So I say that because, like, look at nitrate, NO3 minus versus NO2 minus. Sulfate is SO4 minus 2 minus, sulfite SO3 2 minus. So it's that difference of 1, okay? Now, why I point these out, because you will see these involved in the naming. Because these have a negative charge, these are our anion for the most part that we're going to use in these this naming, with the exception of one particular one I want to point out: ammonium. Okay. Now, ammonium, what you should notice about ammonium compared to everybody else on this chart, ammonium has a positive charge. And so ammonium would serve as the cation in some of these naming scenarios inside the compound. So, like, for instance, if we had like NH4Cl, well, this is that case. Remember, I had said there's like 98% of the time you're going to have a metal present in an ionic compound. This is the 2%. In this scenario here, NH4, there is no metal present, NH4Cl, but you do have a cation present because of the ammonium. And so when you're naming with these, treat the ammonium, that's a fixed charge, right? And so this would just be ammonium chloride. We don't have to say ammonium 1 chloride, okay? And so we'll do some naming practice with that in just a minute. All right, look, I've read my own mind. NH4Cl was the first one, okay? So let's try naming number 2. We have CaC2H3O2, 2, okay? And so let's think about it. Now, we do have a metal present. That ion, while it's more than one element, still treat that as a big blob, all right? So it's like calcium as the cation, C2H3O2, which is acetate, as the anion. And we ask ourselves, is calcium a metal? Yes, it's a group 2 metal, right? It's found right here on your periodic table. So that means it's a fixed charge. And so when we name this, we would have to just name the metal and the anion. Now, this is where, if you haven't memorized these, it will be hard to actually name this, right? And so C2H3O2, if we go back to our chart here, that is our acetate, okay? So we would name this as calcium acetate. We don't need to say calcium 2 acetate because it's always positive 2 charge. And we don't mention the charge of the anion. Okay. Now let's try one more. So we got CuNO3 2. Okay. So NO3, we recognize that's one of our polyatomics. It's nitrate. Copper, that's a metal. Is it one of our fixed metals? Well, find copper on your periodic table. And if you look, copper is actually right here. Okay, it's one of your transition elements. So that tells us it's not one of our fixed metals, right? That means we're going to have to figure out the charge. And so just like we did with the oxygen example, we know the charge of NO3, right? Well, hopefully we've memorized it. So here, nitrate, NO3, look here, has a charge of -1. And so to figure out what our copper would be, well, we do the same math. We would say NO3, well, that's equal to -1. And when you see a subscript outside of parentheses, that subscript is saying how much of that entire block you have. So we have 2 of those nitrates. So the total negative charge would be -2. So if the total negative charge is -2, that means copper has to be, to balance that out, +2. And so when we name this, we are going to say copper 2 nitrate. Okay. All right. Were you all able to get that one? And like I said, these will come a lot easier if you get those memorized. So if you've started that chapter already in your class, again, flashcards, index cards, those will be the quickest way. Front of the card, write the name. Back of the card, write the formula and the sign. Okay. All right. So I think we have time to do one more topic. And this is actually one of my favorite topics, which is around understanding the mole. Okay. And so a lot of times in chemistry, you're going to hear this word, the mole, all throughout, right? There's even a mole day. Okay. And a lot of times students struggle with, well, what the heck is a mole and why do I need it? And what are all these calculations I'm doing with it? Okay. So bear with me. I'm going to try to explain to you a way to think about the mole. And it's actually pretty common. It's a common way we think about other things, right? So the mole is just a way for us to count things, a lot of things, right? In an easier manner. Okay. It's a name that basically anytime you hear that name, our brain should be programmed to know how many of that thing we have. Okay. You're probably like, what does that mean? When have I done this before? Well, have you ever heard of a dozen before? I'm sure, right? Anytime you hear the word dozen, you've been programmed to know that 1 dozen equals how many? Doesn't matter what it is. Anytime you hear the dozen means we have what? 12. Unless it's a baker's dozen, then it's 13. But nonetheless, 1 dozen, we always know that we're counting. That means there's 12. Okay? So, and that could be 12 eggs, or we could say 1 dozen equals 12 feathers, or we could say 1 dozen equals 12 cars, right? Because that makes sense, right? Anytime we've been programmed, we use the word dozen as a counting tool. We use it to say 1 dozen means 12. Every time we hear the word dozen, that means 12. Okay. So hopefully I haven't lost you yet. because I'm going to tie this into how this works with the mole. Now, just because we have 12 of those things, whether it's 12 eggs, 12 feathers, or 12 cars, a dozen of each of them, do they all weigh the same amount? You should probably be saying, nope, Dr. J, they don't. 12 eggs certainly does not equal 12 feathers, and it certainly does not equal 12 cars. Each of those has their own mass, their own weight associated with them, right? And so 1 dozen feathers maybe only weighs, and I'm going to make some numbers up here, like 0.001 grams, right? So that's how much mass of feathers we have. Whereas a dozen eggs might maybe weigh, I don't know, again, completely making up numbers here, just to get the point across. Maybe we'll say that that equals 20 grams of eggs. Again, definitely making it up. Whereas like a car, 12 cars is probably like, I don't know, 1 billion grams, right? Hopefully what you're taking home from here is the fact that they all weigh something different. Even though we got 12 of each, they all weigh something different, okay? Now, if that made sense to you, then the idea of a mole should also make sense to you, okay? The mole is just like the word dozen, where we use it to describe how much of something we have. So anytime we say we have a mole of something, 1 mole of, let's say, carbon, 1 mole of carbon equals a certain number of carbon atoms. And that number is what's called Avogadro's number. Avogadro's number, the 6.022 times 10 to the 23rd. All right. Atoms of carbon. Or if we said we had 1 mole of oxygen, that would be still 6.022 times 10 to the 23rd atoms of oxygen, right? So it's just like the dozen. When we say a dozen, we got 12 eggs, we got 12 feathers, we got 12 of whatever. When we say a mole, we got 6.022 times 10 to the 23rd. So it's a lot of things there, right? It's a way to count really, really small things. But just because we have the same number of those things present, do they all weigh the same? And you should say, no, they don't. Just like the egg and the feathers don't weigh the same, these don't weigh the same. So where do we find the mass of those? Well, the mass is going to come from your periodic tables. And so when we're weighing an atom, we're going to use that molar mass that we find on the periodic tables. In fact, that's why we say molar mass, because it's basically saying it's that much grams, whatever numbers that's on the periodic table, in 1 mole. And so for like carbon, we would say that's 12.011 grams of carbon equals 1 mole. That's just the molar mass, the atomic mass found on the periodic table. Whereas oxygen would be 16 or 15.999, which would round up grams of oxygen, okay? And so hopefully that made sense to you to help you understand the connecting points. Like, what is a mole, right? So a mole is it's a way we count things, really, really small things. And every time we hear we got a mole, if we're asked how many of something it is, it's gonna end up being 6.022 times 10 to the 23rd that we're gonna be using. If we're asked about the mass of it, we're going to connect that to the atomic mass that's found on your periodic tables. Okay, so that's the first part. Okay, now the next part that we're going to think about is, well, how do I use this in these calculation problems, these mole-based problems? Okay, and so this idea, and we're going to build on this idea throughout our live sessions, is probably my hands down my favorite trick or hack when it comes to chemistry. And that is what I call Mole Island, okay? And so Mole Island helps us to visualize what are the steps that I need to do to solve any of these problems. And so how Mole Island works, in the center, we have our mole, okay? That's our base point or our base island. And over here on this side, I'm going to put an island or a blob that represents my grams. And over here on this side, I'm going to put a blob that for right now is just going to represent atoms. Or it could also mean molecules. Or, make it a little bigger, formula units. And we'll talk about what each one of those mean. When do you use those? Okay. Okay. And so the mole island is a visual. It's going to help us figure out how many steps might a problem take. If I want to get to moles from grams or from moles to grams, back and forth, this is where I'm going to be using my molar mass. And so again, the molar mass is simply the atomic mass from the periodic table equal to 1 mole of that thing. Just like the example I just showed you. And for anytime if I want to go from atoms to moles, or moles to atoms, or molecules to moles, or formula units to moles, formula units are used when we're dealing with ionic compounds. I'm going to be using Avogadro's number. So I like to say AB's number. And so that's that 6.022 times 10 to the 23rd of whatever is equal to 1 mole. Okay. There is a top part to mole island, but I'll teach that in a couple of weeks when we get into gas laws, because there's one more relationship we'll think about. The last thing I'll say that we're going to use mole island, and we're going to use the given and find format that I introduced. I think it was the first week we were here. So given and find, remember that's that given. Any units that I want to get rid of go on the bottom. Units I'm solving for go on the top. And you can do as many of those as needed. Okay, so screenshot, take a picture, but this will be the thing that's going to help you out whenever you think about doing these mole calculations. Okay, it should hopefully help you out. Now, what this should also tell you is that I can't directly go from grams to atoms in one step. I have to get to moles first before I can continue on to solve my problem. Okay. And so I often tell my students, when we're dealing with these problems, if you're not starting in moles as you're given, then that's probably going to be your first step, is to get to moles, because that's going to be how we go from one thing to the other. The mole is going to end up ultimately being like our big linking unit that we can use. Okay. All right. So I just gave you a lot. So let's look at this problem here and see how do we put all that together. All right, so in this problem, it's asking us how many moles are in 50 grams of lead 4 oxide. Okay. So a couple things I look at. One is I'm trying to solve for moles. So this is my find. And grams is my given. Okay, so I ask myself, well, can I go from grams to moles in one step? And you should say, if we go back to our mole island, that, yeah, I should be able to go from grams to moles in one step. I know a direct connecting point. So I can set it up with my brackets. So 50 grams of PbO2. Okay. And I want to get to moles of PbO2. All right, so then I have to say, okay, well, I'm going to need a conversion bracket. Well, where do I get the information to go in here? Well, because I'm going from grams to moles, this is where we're going to use that molar mass. Okay, and so your molar mass comes from your periodic table. And so if we didn't have the numbers given to us like we see on the screen, we would go and find lead on our periodic table is 207.2. Oxygen is about 16. And so when we add this up, the mass that we're going to put down here represents all of the atoms that are present in that compound. And so we would have to first add 207.2, that's our lead, plus we got 16 from oxygen, but there's 2 of them. So 2 times 16 to get our molar mass. So we got 207.2 plus 32. And that gets us 239.2. And we would say that's grams for every mole. Again, molar mass, grams connected to the moles. And so now we take that information. That is our conversion factor. So we're going to be plugging this in as such. And so on the bottom, we are starting in grams. So we're going to put grams on the bottom. Grams of PbO2. Always write all your units out. And on the top, we put moles. Just like when we were doing those unit conversion problems 2 weeks ago. Always put the units in first and then put the numbers in, because sometimes students get caught up in, where should I put the one? Where should I put this? Put the units in first, and then that will tell you where everything goes. So now my job is to take this and plug it into this conversion factor. Okay, so I'm going to say there are 239.2 grams in every 1 mole. Okay. And so now we see our units cancel. Grams and grams will cancel. I put 2 grams on there. That grams will cancel. And now we're ready to put in our calculators. So in your calculator, you should be doing a multiplication for anything that's on the top. So 50 times 1 divided by anything on the bottom, hit the division symbol for. And so we'll do 50 times 1 divided by 239.2. And if you're plugging that in, following along, drop it in the comments. What did you get as your answer? Okay. All right, what you should have gotten in your answer, hopefully, is 0.209 grams of PbO2. Notice, my calculator gave me 0.20903, but with sig figs, there's only 3 significant figures here. And so we would stop with 3 significant figures. Okay. All right. Hopefully I didn't lose you. We're going to try one more before we wrap up for the night. And again, I definitely encourage you all to check out that QR code in the top corner. There is an option for you to be able to get a discount or a promo code if you subscribe for a subscription with Chegg. All right, we're going to do one last problem before we wrap up. And this one is going to test us a little bit. Okay. And so here we want to figure out what is the mass. So mass is telling us the grams. So what's the mass of 4.78 times 10 to the 24 molecules of NO2? Okay. All right. And so I see molecules and I see mass or grams. So you should ask yourself, can I do this in one step? And the answer is no. Think back to Mole Island, right? Molecules was over on one side, grams was on the other. So this is going to take at least 2 steps. Okay, I always like to get that visual out first. So I need to somehow go from molecules to moles first, and then from moles to grams. Okay, so this is going to require 2 steps. Okay, so then we set up our math. Okay, and this is NO2 molecules. And we're saying molecules here, not atoms or formula units, because it's not an atom because there's 2 elements present, right? It's a compound. And we use formula units when we're dealing with ionic compounds. So like that PbO2 that we just saw, we would count those in formula units instead of molecules, okay? So then I'm going to set up my brackets to convert. Okay. And I'm going to put my units in. So first things first, my given is NO2 molecules. So I'm going to put that on the bottom so I can cancel it out. NO2 molecules. All right. And remember, my first step is to get to moles. So on the top, I will put moles of NO2. Okay. And then once we're in moles, we can go from moles. So I'm going to now put that on the bottom. And then we can ultimately solve for grams. Okay. And so now we got to think about, well, how are we going to fill this information in? Think back to Mole Island. Remember, when we're counting, we're using Avogadro's number. When we're using the mass, that's where we're thinking about the atomic mass, or that molar mass. Okay. So Avogadro's number, that's 6.022 times 10 to the 23rd. That's how many of these molecules are in 1 mole. And so we would say 1 mole is to 6.022 times 10 to the 23rd. All right, so that's how many molecules. And then for the moles to grams, remember, we get that information from our periodic table. So this time they didn't give it to us. So we got to actually look it up. And so I'm going to go to my periodic table. I'm going to find nitrogen, which is 14.007, and then oxygen, which is 16. Okay. But now we got to add that up and say, well, I have 2 oxygens. So you should be doing 14.007 plus 32. And that gives us 46.007 grams. And that's what we're going to be putting into our bracket. So we would say 46.007 and 1 mole. Okay. So now this is where we're ready to plug into our calculators. Again, anything that's on the top, multiply. Anything on the bottom, divide. And this is where you want to make sure you're putting things, your scientific notation in your calculator properly, using that EE or EXP button that might be on your calculator, depending on which calculator you have. If you're using times 10 raised to a caret 23, you got to put all that in parentheses, okay? Or else you're going to get a really big number, like something to the 47th power or something like that. All right, so we're going to do 4.78 E24 times 1 times 46.007 divided by 6.022 E23. And that now gets us, go ahead and drop it in the chat if you're following along. Hopefully you should get 365 grams of NO2. Okay. All right, y'all. Well, that is just about my time. I hope that you all learned something as we covered the naming of ionic and molecular compounds today, and also got into some mole calculations. This is going to help us out for what my old chemistry teacher used to call the big S in the sky, which is stoichiometry, which we'll get into next time around. But definitely stay tuned. Come back to this platform next week. Same time, 8:30 p.m. Eastern, 5:30 p.m. Pacific time. If you need additional help, definitely hit that subscribe button through that QR code. There is a promo going on right now, 50% off if you're subscribing. And we'll be back here again next week. So until then, definitely drop any questions or comments that you have, and we look forward to answering your chemistry questions next week. Have a great evening, everyone, and we will talk soon.